Hello and welcome to Australia in Space TV. My name's Chris Cubbage. I'm the editor with My Security Media. Today we're across to California with Adam Scraba, the Director of Product Marketing with NVIDIA. Adam, thanks for joining us.
Thanks for having me.
We're going to be talking about Omniverse Blueprint for Smart City AI. I've kept this on our space channel. We do a security channel, Adam, but I noticed that there's some satellite imagery within the context of Omniverse. And we're looking at physical AI. So it's very impressive tech, in terms of looking at some of the videos. We may even have some overlays on this session as well as to what it's doing. Introduce us to Omniverse, and this is looks like a whole lot of plugins to sort of create that blueprint, right?
That's right. That's right. Yeah. I mean, maybe it's probably best if I take a step back and kind of set up a few things. So I think a lot of people are very familiar with the concept of smart city applications, smart city services, things to make traffic management run smoother, make safe spaces more safe. Increasingly, we are seeing very sophisticated AI models and AI agents helping out with a lot of these services. And as the complexity of the AI gets more sophisticated, it becomes very much like almost like an industrial automation process. A lot of the AI agents are there to automate certain things, and this industrial strength or industrial class automation turns out it's not that dissimilar to robotics or true industrial automation. And NVIDIA has been actually in this space for a really long time. Perhaps the first robot that we went off and helped develop was the autonomous vehicle. Clearly, that's a robot. It perceives, it reasons, and it acts. And then we went on and we rolled out, the concept of true robotics platforms that people could kind of understand. Robotic arms, humanoid robots. That's also very much a clear case of automation and robotics. We then went and we deployed the same concept into factories and warehouses, and now into cities. And what's really important about industrial class automation or robotics is that it's really a very much a simulation-driven problem. These models and these applications are incredibly sophisticated, and they need to actually be simulated before they're rolled out. No difference than an autonomous vehicle that needs to be driven billions of miles in simulation before it's at a quality, at an accuracy, a performance level that can be rolled out on the roadways safely. It's the same thing with humanoid robots, and it's the same thing as we're going to be doing in smart cities. And so we rolled out, and also NVIDIA's really lumps this into a concept, an effort, a movement that we call physical AI. And physical AI is very much you simulate AI in a digital twin. You train a model. You give the AI a kind of literally like a gym to work out and to refine itself to get better. And then you roll it out into a runtime, into a runtime application. So there's simulation, there's training, and there's runtime. This is sort of three computers, and these three computers are actually connected, all together, interconnected in kind of a circle of life. So that's what we consider physical AI. So with this Omniverse Blueprint that we just announced and we just rolled out, we are bringing physical AI to cities for the first time. And so it's incredibly powerful. And as I mentioned, these AI agents like traffic, ITS, intelligent transportation systems, they are incredibly AI. They're sophisticated AI, and they need to be simulated before they're deployed. It's perfect for that. We've got partners that are rolling this out for things like flood detection, mitigation. And in each one of these cases, it's perceive the world that's happening, perceive the situation on city streets, reason against what's happening, what happened, what might happen in the future, and then act. And that is hopefully do something that'll improve what is about to happen next.
Well, that was going to be one of my first questions, is the creation of that autonomy there and creating and solving problems, I suppose. Is it looking for the problems? Because sometimes from the human concept, they might not be, we're not aware, in terms of what we know and what we don't know, where the system may well find solutions to problems that we're not necessarily seeing. The other aspect is it creating that? Is it starting to look for solutions to problems automatically?
Yeah, it is. I think we're you know the concept of that as I mentioned, perception and then reasoning. And by the way, reasoning kind of means what happened, what's happening now, and then what might happen next. I think that we're on a continuum and a journey a little bit, and then also obviously the action, like what should I now do? I think that we're still on a continuum. I think that really, our team has been working on this for about 10 years, and in the first, probably 5, 6, 7 years, we really were trying to resolve and work on the perception. The what happened or what's happening now. I think where we are with generative AI, where we are with the combination of vision language models, VLMs, LLMs, RAG, all of this brought together is really helping us perceive reason and in terms of it, and even predict what might happen. So yeah, to answer your question, that is the goal. I think that depends on the sophistication of the developer and the solution partner. There are companies that are definitely headed in that direction where they can predict what might happen and of course come up with a mitigation plan.
How separate is the vision language models and the large language models? Are they coming together, or are they still kind of separate streams of data? And I'd also imagine the video and the vision is much richer, so there's a lot more sort of power required to understand and learn from that. But yeah, where is that on the trajectory? Are they coming together? Will they be together eventually?
Yeah, it's a good question. It's hard to say. I think really right now they're arguably separate. VLMs are kind of this class of model, and then LLMs are a class of model. And I think for those of you maybe who aren't familiar exactly with a VLM, if you can imagine in the old days of computer vision, you'd have an image, and then you'd say, is that a cat or a dog? And then the CNN would put a bounding box around, that's a cat with 90% accuracy, and that's a dog with 96% accuracy. That's kind of old school convolutional neural network technology. Vision language models, you give this model a video and you say, summarize what happened. Tell me what's going on. And it'll say, for example, this is a classic kind of a silly one, but what's the difference? A VLM can identify really bad dancing and maybe violence, for example. Which is a nuanced thing. But that's the concept is these models have the ability to understand very nuanced actions and make sense of it. And so a VLM is akin to ChatGPT for vision. Summarize what happened or ask a question. What did the shopper on aisle 3 do at 2 p.m. and it'll be able to answer that question. So there is a language component to a VLM, and there's a vision, physically what happened. And I think what's really exciting, super exciting, is that where we're headed with a lot of the models that NVIDIA is working on, they're bound and they're inherently built on physically accurate actions. So unlike the old days when somebody might say you could ask a question that was sort of approximately what happened in a scene. With models that are based in the physical world, there's a physicality to it, and it makes the accuracy of its explanation of what happened really high. But hopefully that answers the question. And I think perhaps your other question was, that they're compute intensive. Yeah, they are compute intensive. These models now, the optimizations and the refinement is a very quick evolution, and we're seeing incredible strides being made in this space. These models used to take a lot of GPUs, and now we can run them at the edge. In some cases we can run them right at the edge on a workstation, on a small device like a DGX Spark, all the way down to to a smaller Jetson model. So we're seeing a lot of optimizations. And I think the other really important thing to note is that VLMs can now be fine-tuned for a very specific use case. So I think we're all familiar with big models like ChatGPT. They're inherently built to be generic. Everyone, my uncle, my son, we can all go and use it. But with these models, we can now fine-tune them and make them very, very bespoke for their use case. And that's super important, of course, in what I call industrial automation, which might be truly industrial or smart city focused.
I've got about 3 questions coming up in my mind. I think maybe the data sets, because then that might sort of lead us to the edge computing required, because from a video perspective, in one of the companies I noticed within the ecosystem here is milestone systems. So, I imagine bringing all that video back to a central sort of server and then analyzing it would be too much. It's all about the edge computing, and same with robotics and the vehicles. It's just too much, even on the network side. But yeah, what are the data sets here? And maybe back to Omniverse Blueprint in terms of the digital twin. Is there any limitations on data sets, and hence the Australian Space Channel here with satellite data and updating that imagery as well?
Yeah. So maybe I'll start by saying that to begin with, there's for training of these models, and let's just focus on VLMs, because I think in the world that we're living in, particularly in the smart city blueprint that we're talking about, a lot of it is using a camera as a sensor, and therefore the model is looking at imagery or video, and so then it's going to be a VLM. So a VLM with most models, there's a thing that's considered pre-training of the model, and there's post-training. So imagine you have a model, but pre-training is considered all of that corpus of data that it could be thousands or millions of hours of video or millions of images to train a very important model. Milestone Systems, for example, has done the pre-training for a model that they're going to release to the world that's focused on traffic. And so they got all the huge amount of data, and I'm not actually exactly sure how much data they had, but they had to craft and create a ton of data, and they happen to be in that beautiful space where they have all that data. They created a lot of this incredible, they took all this GDPR data and they crafted a model out of it. And now if you take that model that might have been trained from data in Denmark, and you want to go and deploy that in Singapore or Kuala Lumpur, for example, that's the roadways are going to look a little different. The actions are going to be different. And so there's this thing called post-training. So you take this massive model, and then only with maybe 10 videos or 50 videos, significantly less data than you use to train that massive model, you take that small amount of custom data and you do post-training, and you train that model. And now it's the accuracy for the model that was previously trained for Copenhagen now works beautifully in Singapore. And that's I think the world we're now in, is that a lot of local partners will take that model and they'll post-train it, they'll fine-tune it for their environment, and they'll go and deploy it. So that hopefully describes the training process. But now let's get back to digital twins and Omniverse, and you mentioned aerial data. So part of, for example, taking a model and deploying it in Singapore, the roadways, it's very helpful to have a digital twin. And when I say digital twin, a lot of people in smart cities have digital twins, but largely their digital twins are visualization platforms. It's a way to, their digital twin might be a 2D map, and with a little, lights bleeping of where there's traffic congestion, for example. When we say increasingly digital twins for smart cities, particularly as it relates to Omniverse and the blueprint, the Omniverse Blueprint for smart city AI, we talk about sim-ready digital twin. And that means a 3D photorealistic digital twin of a city where you can run a scenario. You can have cars going, pedestrians walking, and it's photorealistic, and it's actually representative of a street corner in Singapore, for example. Now, what we can do is, if it's photorealistic and it's geometrically accurate, we can actually we can create a virtual camera on a street corner, and we can press record on it, and we can run a simulation, and there's traffic flowing and there's pedestrians walking around, and we're actually capturing a virtual video stream. And if we apply Cosmos transfer to it, and we apply some other sort of post tools to it, we create a video stream that actually looks incredibly. You would have no concept that it's a simulated video stream. We'll use those video streams as the customization data sets to go and post-train that model, if that makes sense. So hopefully that tries to connect it all together. Now, one of the other really important things to note is that pretty much every city has a digital twin. And I think where we're headed is that cities are increasingly realizing, and this does not need to be a digital twin of the entire city. In a lot of cases, there's a a crawl, walk, and a run that's happening. The AI models, for example, the applications, the smart city applications can be small. You know, a lot of partners want to deploy maybe at certain really important intersections, and they want to maybe deploy traffic monitoring and management applications in just a few intersections. And then their digital twins, their photorealistic sim-ready digital twins, can also be just focused on these very few intersections. So there's a way that a lot of, you know, to test and try out these applications, people can crawl, walk, and then run, and focus their efforts on a small set of really important bottlenecks, perhaps when it comes to traffic or other bottlenecks in the city, and then scale up as appropriate.
And just to clarify, so the Omniverse Blueprint is the visualization of that from a city perspective, because then there's other deployments like robotic fleets and the like. I can see it's being used in factory and manufacturing. So again, you can sort of create that real time. Well, that's a good question, is how real time can you get this in terms of data sets coming in, particularly from video, versus looking at a digital simulation?
Yeah. So let me, maybe first I'll describe kind of what's included in this blueprint. So this blueprint is the purpose, the mission, the soul of it is to create that AI gym, as I mentioned, the space in which to exercise and to nurture and to train all of the AI models that you may have. And so for example, in order to do that, let's just focus on, you know, we could go back to the example of Singapore. If there's just, even if we focus on one intersection, this blueprint allows you to take, a lot of cases, people have aerial footage or aerial 2D imagery. You'll have a partner that does mapping because they can identify where the lanes are. You'll take maybe a partner that has some maybe LiDAR scan, a 3D point cloud of that intersection. And this blueprint helps to bring it in to an Omniverse sim-ready digital twin. So truly a 3D geometric, physically accurate model of that intersection. So that's one aspect, that just to get to prep the digital twin to be able to be simulated. Then we give you the tools through this blueprint to instantiate vehicles, pedestrians, for example, because we're talking about that intersection. And we allow you to hit play. We allow you to create a simulation, and you simulate a traffic jam, and you can simulate it. We also then give you the ability to instantiate these virtual cameras. And on those virtual cameras, after you hit play for the simulation and all the pedestrians are walking around and there's a traffic jam, you can hit record on the camera stream, and the camera stream now gives you video streams. Also in this blueprint, we now give you the ability to use that video stream that was generated to then go and train models and refine them. And and that uses, that there's a RTX sensor. We pull that data. Some of that data might go through Cosmos. Cosmos is the magical tool that allows us to create a breadth of physically accurate photorealistic videos that might be that intersection in rain, with glare, all sorts of scenario nuance that to diversify our data set. And then we use NeMo to go and train the model, and we deploy that model through a Metropolis agent. So it's really completely all of the simulation training and runtime, all those three computers in that circle of life. And it's very similar to, and I'll just say one more thing. It's very similar to a blueprint that we recently also announced and launched, which is called Mega. And Mega is the same concept. It is meant for the same training and nurturing of AI agents, robotic fleets in factories and warehouses. Yeah. And so this is very akin to that, but built for cities.
One last question: for the business case here for, I understand, for cities, and sometimes they are a bit cash strapped as well in terms of what they're doing. And you talked about, I'll call them applications, those different applications with different capabilities. What's the business case? Is this something you can modularize and build over time and sort of practice? Because again, the skill sets required. So yeah, what's the business case for the client? Can they modularize it? And then what type of skill sets would they need to have on their team?
Sure. A lot of the partners, a lot of the cities that are rolling this out are finding incredible reduction in costs. So whether the costs are people stuck, perhaps stuck in traffic, It allows the cities to reduce the amount of waste they have. One of our really first early adopters is in Kaohsiung City in Taiwan. And they found that by leveraging this blueprint, previously, and many cities are like this, they have very strict silos of data within the city. By using this blueprint, they were able to unify all of the data silos across many different agencies within the city. And the combination of being able to leverage the data across city planning, waste management, disaster recovery. This reduced a lot of waste and reduced costs for them. And also what we're seeing is that we have a really robust partner ecosystem that goes and already is selling many of these services into cities, whether it's traffic management or flood management. And so a lot of cities are actually paying for some of this technology already. We're just making it a lot better and a lot more efficient to go and deploy. And with a rich ecosystem of partners, whether it's a GSI like Accenture or Deloitte, we've got solution delivery partners, we've got a whole section of software partners that are all selling this kind of technology to cities. There's significant cost savings that are going to happen soon.
Well, it is very exciting. It's a great. We'll definitely have some video overlay because, again, I think it's not until you visualize it. We're talking about sort of digital twins and visualization. It's not until you visualize it you get a sense of, wow, okay, those data sets are quite incredible. And then again, it's just up to your imagination and your operational requirements on how you deploy it. This is also in the lead up to our Indo-Pacific Robotics, Automation and AI conference in Cyber in Perth, 7th to 8th of October. So hence having a strong interest in this, Adam, and how we bring all that together. But Adam Scraba, the Director of Product Marketing with NVIDIA, thank you so much for joining us today on Australia in Space TV, and enjoy the rest of your evening.
Thank you so much. Thanks for having me.